Hey again, AP Calc students, time for another FRQ. Today we are looking at question number 6 from the AB exam from the year 2014. So number 6 means no calculator, and if you look at it briefly, you notice a big slope field jumping out at you. So this is definitely going to be a differential equation. The only thing we have to investigate is whether this is a differential equation that's solvable or not. So let's see what we have here. Consider the differential equation dy dx is equal to the quantity 3 minus y times the cosine of x. Let f of x be a particular solution to the equation with an initial condition of 0, 1, or f of 0 is equal to 1. The function is defined for all real numbers. So if you glance at the slope field, it definitely has a feel of something sinusoidal, so not surprising there is a cosine as a part of the differential equation, which means the original, if we integrate, it's going to have a sine in it instead of a cosine. And so we don't have to generate a differential or generate a slope field. We have to read one. So it's usually one or the other. So if you know how to read a slope field, this is actually a fairly easy question. So let's see where we start. According to the question, it says a portion of a slope field of the differential equation is given below. Sketch the solution curve through the point 0, 1. Now, usually on the test, whatever point they give you, they will actually highlight. For whatever reason, they did not do that on here. So we can go ahead and do that, and we'll put a point here at 0, 1. So we're going to have to sketch the solution that goes through that point right there. Now, if you're interested, you could pick a coordinate somewhere where you see a tangent and see if it's working. Something that jumps out at me, if you notice right up here at 3, do you see how all the baby tangents here, all the tangents have a slope of 0? So, since our differential equation is the formula for the slope of the tangent, so our slope is equal to our differential equation, and they give us 3 minus y times the cosine of x. Well, if y is 3, that's going to make this 0. So that's very logical that we have slopes of 0 all the way across at 3. Now, the other thing you might want to quiz yourself on, if you remember your unit circle, where is cosine 0? And cosine is going to be 0 at the top and bottom of the unit circle. So at pi over 2 and 3 pi over 2. And those aren't, nice clean values on the graph. But if you said, well, pi over 2, that's about 1.57. We should theoretically have a baby tangents with a slope of 0 there as well. So let's see if we do. If we went to 1.7, there's 1, there's 2. 1.7-ish, now that's not a perfect spot where they decided to draw the baby tangent, but you can definitely see that the slope is, they're peaking there, somewhere in there. So the slope field's making sense. But what we have to do is just read it and going through the point 0, 1. So let's see if we can do that. We'll start at 0, 1, I'm going to move to my right. So as I move to my right, it looks like the slope field is telling me I need to start going upward. And so I'm going to go upward, and I'm going to continue to go upward. And as I move over, it looks like these tangents are telling me to keep increasing, but not at quite as steep a rate, and I just keep connecting to the next value, and I'm going to peak somewhere in here, and then it's actually each one is telling me to come back down. Okay, and so you have a little bit of room for error here, but in general that's the behavior, and just follow the tangent at the next x value and just do what it says to do. So now I'm going to move to the left here, and it looks like I'm definitely going downward. But as I continue to go downward, I'm running into, this one is definitely a little steeper here. If you notice, these tangents are pretty steep. And it goes to a little steeper of a point right here, and then it comes up a little bit more aggressively. It looks like something like that. And so this one was a little more gentle, almost like a upside-down quadratic here, but this one was a little bit more aggressive. But that's, in general, what you've got. And so you just read your tangents and go increase or decrease at approximately the rate that it's implying with its tangent. So you just sort of trace one tangent, connect one baby tangent to the next one, and you get this kind of behavior. So that was 1 point right there. Just can you sketch a function based on reading a slope field? Okay, let's move to part B. Part B says, write an equation for a line tangent to the solution in part A at the point 0, 1. So actually this point here, we're going to write the equation of a tangent that goes through there. We could probably guesstimate it right now. The slope's probably about 1, maybe a little steeper, and the y-intercept is already 1, and then we're going to use that equation to make an approximation. So here we go. We've done this several times, and they like this question here. So y equals mx plus b, or the point slope version, y minus y sub 1 is equal to m times x minus x sub 1. So they've given us the coordinate 1, 0, or 0, 1 rather. So 1 is equal to m times 0 plus b. So on this one, I've already got my y-intercept as b. Already have that. And over here, looks like we have y minus 1 is equal to m times x, because x sub 1 is 0. So we're that far. And now what we're going to do is actually substitute in the slope. So, a fundamental concept here in calculus is understanding that slopes are equal to derivatives, and which are equal to differential equations. So you go here and you just say, well, here's my slope formula right here. There it is, and so if I evaluate this at the given coordinate they gave us, which is 0, 1, this should be fairly straightforward. So I think we're going to solve this, but we'll move this over here so we can see that. And I'm going to rewrite this differential equation. We can sneak that in right here. So we had dy dx is equal to 3 minus y cosine of x. And we're going to evaluate that at the coordinate 0, 1. So at 0, 1. So my y value is 2. So again, I'm going to write this little notation here, 0, 1. And so that's going to give me 3 minus 1, obviously 2, and that'll be the cosine of 0. So as we simplify that, cosine of 0 is 1, 2 minus 1 is 2, so this is equal to 2. So it looks like our slope is equal to 2 at this coordinate. So now we've got it, we can sub it back in. So in this format, point slope, you could have had y minus 1 is equal to 2x. Could have written it that way, you'd probably move that 1 over. And then in slope-intercept form, we are back to y is equal to 2x plus 1. And you can see these are the same. Now, they say use that to approximate f of 0.2. So if we say, well, f of 0.2, that's going to equal 2 times 0.2 plus 1. 2 times 0.2 is 0.4. Add that to 1, you're going to get 1.4. Okay? So there was the tangent line approximation, or the tangent line, and then approximating a value close to the point of tangency. That was B. Now, like most of these questions, the bulk of the points goes to, can you solve a differential? And when we began, the question oftentimes is this a differential equation that is solvable? And this one is. You can separate your variables, but it's a little bit messy. So let's take our time going through here. So we've got dy dx is equal to 3 minus y cosine of x. Separating the variables, that's going to make this dy over 3 minus y is equal to cosine of x dx. Okay. If you want to throw parentheses around the bottom, you can, that's fine. But now we're going to have to integrate here. I'm going to make this 1 over 3 minus y dy, just to move that out. And we're going to get the integral of cosine of x dx. Okay. So again, here with having a trig function, we have to integrate here. This is you just got to be careful. Sines and cosines, you can get easily burned by the negative. So just check your work by taking the derivative. So remember, when you take the derivative, you change the sign. So the derivative of sine is cosine, but the derivative of cosine is minus sine. But I'm integrating. So my integral result would be just sine of x. And again, check your answer with your derivative. So this side's just going to be sine of x plus c. Derivative of sine is cosine, we're good. Now over here, this is, got to be careful here. This is not difficult, but you do got to be careful because you're going to have a negative coefficient here that gets generated. For some of you, you're good enough to do this in one step, but I'm going to put all the work over here. And whenever we're solving differentials and we have a u sub, we wind up putting our u sub to the left, which looks a little weird, but we can do that. So I'm going to let u equal 3 minus y. So in transition here, I'm going to have 1 over u, and this is where you got to be careful. I have 1 over u dy is equal to this. Well, when I take my du, I get a negative dy. So that means negative du is equal to dy. So when I do my substitution, I got to bring in a negative. Got to be careful there. So what I wind up getting here is negative the integral of 1 over u du, and I haven't done anything to the right here since the sine of x plus c. Well, now you should be able to recognize this is going to be a natural log with a negative out front. So I have negative the natural log, and I'm going to put u back in just to save a step here, and u was 3 minus y is equal to sine of x plus c. Now, this negative is potentially problematic here, so I'm going to give you a hint here how to work around that. But before I do that, I just want to solve for c and get that out of the way. So if you recall, the coordinate in the problem here, we're doing this at the coordinate 0, 1. So let's go ahead and substitute those in and see what we wind up with. So over here we get the negative, the natural log. This was 3 minus 1, so that gives us the 2 here. And then the sine of x, that's going to be the sine of 0, which is 0, and that's equal to c. Okay, and so now that we've got this, and just so we don't lose anybody, we'll put this in here. So we get the sine of 0 plus c, and yeah, just not worth the confusion if anybody's getting lost here. So we have 3 minus 1. Okay, and so then we get natural log of 2 is equal to c. Okay, so I'm going to take this value here, and I'm going to go back up to this step and rewrite that. So I get negative the natural log of 3 minus y is equal to the sine of x minus the natural log of 2. Okay, and 2 absolute value 2 is fine. Okay, now it's here that I want to give you a little trick here. Now most of you guys would, we have to solve for y, and y is trapped inside a logarithm, so you're going to have to Roman numeral 9 it to rewrite it as an exponential. But before we do that, it's a little bit, this negative here creates needless difficulty in that process, so I just want to move it. So let's multiply everything by a negative before we do that, and it will make life much better. So it's going to be the positive natural log of y is equal to negative sine of x plus the natural log of 2. Okay, now we can Roman numeral 9 it. Remember, this is this base of e, so what winds up happening is we get e to the negative sine of x plus the natural log of 2, looks weird, equals 3 minus y. Okay? We write it as the exponential. So again, remember, for those of you that are maybe don't recall this, when you get natural log of x is equal to y, for example, remember e is my base here, so I'm doing e to the y is equal to x. That's the Roman numeral 9. So e to the other side is equal to the argument, which isolates over here. Now this step right here, this has come up a few times. This is a pre-calc algebra concept here. If you have a sum in your exponent, you can rewrite it as a product, which I'm going to do right here. So this is really e to the negative sine of x times e to the natural log of 2. That's a totally legit step right there. And I still have this 3 minus y over here. Well, another property that hopefully you remember, e to the natural log of something is just the argument. And so if you remember from pre-calc, sneak this little rule in right here. Give us room to work. For example, if I gave you 2 to the natural log base 2 of 5, if the base of your exponent, if your exponent is a logarithm and the base of the logarithm matches the base of the exponential statement, it just equals the argument. And so we have e to the natural log, which is log base e, of 2. So that's just equaling 2. So this whole thing goes to 2. So I get e to the negative sine of x times 2 is equal to 3 minus y. So I'm going to add the y over. I'm going to bring these guys over here. And so what winds up happening is I get y is equal to 3 minus 2e to the negative sine of x. if you decided not to get rid of this negative, you create a real headache for yourself. So just remember to do that, and that'll save you some. Now, some people also would have factored out a negative here and integrated negative cosine, which would have given you a negative sign. That was another way to deal with it as well. But just be careful when you've got negatives out in front of logarithms. When you rewrite as exponentials, it can be needlessly confusing. So there it is, kind of not the simplest differential equation, obviously, with a sinusoidal and a negative and a natural logarithm that produced a negative there. But that's how that one is. Take your time going through that one. But that was 6 points. Unusual that you get that many points on that one. It's because it was just 1 point for A, 2 points for B, 6 for C. Okay, another differential equation, and that is 2014 number 6. Thanks for watching. We will see you next time.